Hi, this is Mark. This is going to be the last set of this series covering a Calculus 2 midterm exam, and I'm going to cover problems 13 and 14 for this set. For this problem, we're evaluating the indefinite integral of 1 over x ln x dx. For this case, what we need to do is, for this case, we're going to use UV substitution, so it's integration by substitution. So to start, we notice that if we take the derivative, say ln x, and we do prime, this gives us 1 over x. So when we take the integral of 1 over x, so this is like integrate, and then this is the direction of the derivative, derivative, and then integrate. So it basically reverses the direction. So for this case, we want to go in the direction of, notice how there's this ln x into 1 over x. So we want to get 1 over x. So if we let u equal to ln x, then du with respect to x equals to 1 over x. So that means du equals 1 over x dx. So we took care of the 1 over x dx component, and we also have 1 over u for the 1 over ln x. So we know 1 over u is just 1 over ln x. And we also know, so we have du. So therefore, putting these together, we know that 1 over u times du equals to 1 over. So basically, we're going to start with the du component. So this is like du, and we're times by 1 over u. So 1 over u is just 1 over ln x. We're combining them. Because what we end up having, if you take 1 over x and you combine with 1 over ln x, and we have the dx outside, well, this is equivalent. These are equivalent forms. So we're basically taking now this integral. So we have the integral of 50 to infinity. So we have 1 over x ln x dx. So this can be equated to 50 to infinity of 1 over u du, which equals to ln u from the limits u1 to u2. So basically what we're going to do right here is we know u1. So essentially when we take these new limits, we got to do it as a function of u. So u is ln x. So we know u. So basically now we're going to take so the limits. So u1 is going to be equal to ln 50. Because basically, if we plug in ln x, we're just going to put back 50 to infinity, but we're taking this as a function of u now. So if we take u2 equals, well, for this case, what we're going to do actually, we have an issue here. So what we're going to do is we can essentially take a new limit. We can let it equal to, how would I put this? So we have that case, but in this case right here, if we put back ln and we put ln x into here, so we basically put back our limits, 50 to infinity. But what we can do is essentially we're taking a limit of this case. So what this equates to, we can also, right, we take the limit as let's just say b approaches infinity of so we're going to start with this upper limit. And the key here is what we know about this relation when we're focusing on this upper limit. This is where this is where the problems occur. Of course, we can solve for ln 50, but when we take a function ln x, key relation here. So this is like y. Let's think of y-x-axis. Now we have ln of that function. So typically what's happening is these are our this is our output points. So essentially what we're doing is we notice that this function, if we go in the y direction, it tends towards infinity. And if we go as x tends towards infinity, ln x tends towards infinity. It keeps going, it keeps going. So basically these outputs on this y-axis keep going towards infinity. If I keep going, even though the function gets, small, it seems like it's getting less and less, it still continues and continues and continues, and it always increases. It's always increasing. So the big key here is all we're doing is alternating now the y-axis for the new x-axis. So basically we're going to take now the y-axis, which is what we have right here. We're going to define it as a new x-axis. Now we're going to define a new axis right here. We can just call this the y prime. It doesn't really matter. I could call it any variable I want, but just know y prime is now the new output. So this is y prime equals ln. Well, we know ln x equals to y because we defined y equals to ln x. So we just did a substitution right here. So this is ln y. But we know that this goes to infinity. So therefore this goes to infinity. So the output tends towards infinity. And we're defining a new, ln function. And of course, as we, but one thing we notice is the problem with this, we're measuring from 50 to infinity. So that's the key pointer. 50 could be somewhere here. So we're constrained actually. This function is constrained anywhere beyond this limit right here. So basically we're going to the right here and we're going anywhere above this. So that's the key information because we know ln cannot be defined for negative values. And because we know this is ln 1 right here, which is 0, and 50 is going to be greater than 0. So the y value is positive. So basically we're going to start with, because we constrained it, whatever this value is right here. Let's just say y50. And, we can start at, let's just say y50. And when we input the new ln function, well, because y50 is greater than 0, we know it's going to be somewhere positive. And we know we're going to continue the function just like an ln function. It's going to follow the same function and it's always going to increase. So basically this is our limit point. We start with inputting ln because right here it's like ln 50, that's our lower limit. And then we'll keep going towards infinity. So it follows the same function as an ln x. We're just changing now the y values right here become, it's taking any real number right here and we're just changing it along this axis. So in this case, we know as it goes towards infinity, the y direction tends towards infinity. It's always going to keep going. It's going to keep going. It's going to keep going. And it's always going to go in this direction towards infinity. So therefore, we know the limits as b approaches infinity of ln b is infinity. It basically does not exist as a point. So essentially the key here is, because that does not exist, we know this limit. Therefore, if we take of the integral of how would I put it? Well, actually, I think this is all right. So the key here, we don't have to write that, is that when we take and we know this is just ln x from 50 to infinity. Well, because any value infinity and you subtract any value from here, you're essentially going to get still going to be infinity. So this basically converges, it approaches infinity. And the reason for that is, of course, I graphically illustrated when I drew y prime and y, and we start at, we took y50, this point. Well, if we're finding the area, which is this integral, logically it's basically going to keep, if this goes towards infinity in the y direction, it's going to keep adding up infinitely. The area is going to go towards infinity, and therefore this limit does not exist. So that's this key. Anytime you evaluate these integrals, it's important to understand the behavior of the function and be able to analyze that, because then you can always figure it out, even if not necessarily you could maybe evaluate the integral. The best you could do, like if you're not able to evaluate it directly, is you can kind of gauge it based on the behavior of the function and get somewhere. That's the key with, I think, calculus 2. It's sometimes there's tricks involved, sometimes there's all these different tools, and it can be very hard because nowadays it's we have to focus a lot on like memorization, but I think that academics should get away from that, and because mathematics is very broad and it's not based on just memorizing formulas, even though of course if you have a larger repository it's easier to work with these problems, because calculus 2 is, there's going to be a lot of tricks involved and a lot of manipulation and a lot of and just because you manipulate doesn't necessarily mean you have the conceptual grasp. So I think it's just key to have both elements. Of course, you have to have the tools when needed, but also try to understand the behavior of functions, because that's where calculus is essentially involves. So now we're going to go on to next problem. Okay, so for this case, it says for the following two sequences, give the first 5 terms of the sequence in one and determine if the sequence converges or diverges. Okay, and then show detailed of L'Hopital. You don't necessarily have to use L'Hopital's rule like in all cases, unless you have like infinity over infinity or 0 over 0. But you can always analyze these sequences without using L'Hopital. You got to use, I like to focus on you focus on what the numerator represents in relation to the denominator, and I'm going to show you how to utilize that later. So we start with 1. So we're going to take s of n. We know this is sine n pi over 2 over e to the n. So we're going to just do n equals 1 to 1, 2, 3, 4, 5. So we're going to solve these first terms. So if we take s1, we're going to get sine pi over 2. That's 1 times pi over 2 is pi over 2 over e to the 1. But notice how on a circle, so if we focus on these two areas, this is sine pi over 2, which is 1, and this is sine 3 pi over 2 equals to -1. And then right here, if we take sine 0, because that represents 0 is 0, and we take here is sine pi is 0. So key is, as we add s2, we notice now we get sine 2 times pi over 2 over e to this e2, and this is just sine pi over e squared, which we know is 0 because the numerator is 0. So basically for all odd numbers, s1, s3, s5, we're going to get a oscillation. It's going to oscillate between pi halves to 3 pi halves. Pi halves for s1 to s3, s5, and so forth, and now all the even values are going to be 0. As you can see this pattern right here. So s3 is going to be sine 3 times pi over 2 over e3, which equals sine 3 pi over 2 is -1 over e3. Okay, this we forgot to mention 1 over e3, e1. 1 over e, notice how it's this corresponds to the index, and it oscillates between -1 and 1. And then we have s4, which again we know is sine 4 pi over 2 over e4, which is again, this is 2 pi, which is again at right here. This is a 2 pi mark, so that's going to be 0. And then we have s5, so for 5 pi over 2, this is 1 pi over 2 right here. This is 2 pi over 2. Here's 3 pi over 2. Here's 4 pi over 2. And 5 pi over 2, we're back to where we started at 1. So basically this again with oscillation. Okay, so we have those 5 terms. So then we have s of n from n equals 1 to 5. We can put this in a set. So we put it in 1 over e, 0, -1 over e3, 0, 1 over e to the 5. Those are our 5 terms. Or these are the set. Now we need to figure out whether the sequence converges or diverges. Now we know this as a function. So we're going to take the maximum as 1 over e, because that's the first term. And then we're going to represent this as -1 over e. What we notice is the first term is here. Let's just say this is n. Or this case, well, this is 0. Let's just say, because I believe we started, it says start at 1, okay? So we're going to start at 1, 2, 3, 4, 5. Okay. The key information here is we start at this value right here. But then when n is 2, we hit 0. So we're going down. But then when n hits 3, notice how we hit a value less than, because negative 1 over e, we know that e1 is less than e3 is less than e5. You notice how it's all the odd numbers. Therefore, 1 over e1 is greater. We're flipping it because when a denominator goes here, they're getting smaller. And we keep going towards infinity. So therefore this is greater and we get a value less than this. So then we're going down to a value less than this, but then we go back to 0. Or, oh shoot, I screwed up there. This should be right here. So ignore this. Ignore this. So the next point is right there. And then the fourth term is 0. And then this distance we call, of course, this is, 1 over e3 positive if we take the absolute value. And then we're going to take a value smaller. 1 over e to the 5. So then we go to the something like this. So notice how we go and basically what we're going to do is we're going to keep projecting, but it's going to get less. 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 And we notice we keep going and it converges to 0. And this is evident because the terms get smaller and it oscillates between negative and positive, but it gets smaller and smaller, and therefore eventually we converge to 0. So S of n converges to 0 as n approaches infinity. So that's the key information there, is just understand the pattern and how it functions, or the behavior of this as a function, and then that's much easier, I think, to be able to figure it out. And you don't necessarily have to use L'Hopital rule, and especially this case because we don't have infinity over infinity for any of these cases. If we wanted to use L'Hopital, we'd have to have that case, or 0 over 0, which we don't. We could manipulate to get there and maybe figure it out that way, but to me that's unnecessary, when you just know the trajectory of the function and be able to solve in a different way. There's many ways you can solve this, but the key is like understanding the trend, and with sequences and series, it's about whether it converges. Basically the key when you find if it diverges is it either goes towards infinity or goes towards negative infinity. It just blows up, and you can never, and that's where I'm going to get into the next problem, where for this one we're going to focus on the numerator now in relation to the denominator. So for this next problem, so last problem, and we're gonna not so we have S of n is a function of ln. Okay, so we're not going to focus on ln right now. We're going to focus on what's in between here. So basically we have numerator. So we have the numerator. I'm going to do something. I'm going to just a little bit less. So I'm going to make it a little bit finer. So we have numerator. So we have 4n squared plus 3n minus 1. And then we have denominator. So So we have 3n squared plus 1. Notice now we can represent the denominator or numerator as a function of the denominator. For instance, notice this is 4n squared. Okay, we got 3n squared, which is 1 less. Notice that 3n squared equals to 4n squared minus n squared. Okay, notice here we have 3n, but we don't have an n variable right here. And we have negative 1 here, and so we notice also negative 1 is just 1 minus 2. So right here, what we can do is we can represent now the numerator as a function of the denominator. So what we can write is the numerator. Let's let this be, we can add capital N and let the denominator be D. So basically now the numerator equals to the denominator. So the denominator, we're just doing 3n squared plus 1. And then we have to get the 4n squared, we just have to add n squared. Because 3n's included in the denominator and 0's included, we don't have that included. We have to do, we have to add the 3n. 3, this should be n. And then from there, we notice that negative 1, which is right here, and the denominator is just equal to the numerator, or I mean the denominator, which we have is plus 1, so then we have to do minus 2. So we took the minus 2 right here to get to where we need. So the biggest thing is we're adding, so this is of course plus, let's write it out again. So it's n squared plus 3n minus 2. So notice so if n is 0, for instance, so as n approaches infinity, what we notice right here is that this function right here approaches infinity. So therefore the separation, so like if we take, let's for instance say like because this is from n equals 1 to infinity. So like you start with the base case, n equals 1. Well, n squared plus 3n minus 2 equals to 1 squared plus 3 times 1 minus 2, which is equals to 2, which is greater than 0. So what we can do is, where we represent this, let's take this equal to the denominator. Well, in the first case, this is a numerator, and this distance right here is 2. So this is n equals 1. But now let's go down the cases. So as n tends to infinity, so now notice now, like let's say the numerator's over here, denominator is going to be over here. Let's just say this case is like you know, n's greater than 1 somewhere. So basically the distance is becoming this is the distance, because it's equal to the denominator plus this whole distance to get to the numerator. This is approaching, it's getting larger and larger and larger. As this is n tends to infinity, this distance tends to infinity. Therefore, we know the numerator is going to be much larger than the denominator, and therefore we can write 4n squared plus 3n minus 1 tends to infinity, as n tends to infinity. Because this explodes, the distance gets larger. This is floating, and this is staying essentially static, or it's basically the values are getting larger and larger. So for instance, like we have S1, which we just calculated was we can write 1, so this is like 4 plus 3 is 7, minus 1 is 6, and then this is over 4. S2, if you want to write it out, we got, okay, 4 times 2 squared is 16, plus 6 is 22, minus 1 is 21, over 4 times 3 is 12, plus 1 is 13. Notice the difference. We have from 4 to 6, this distance is 2. From 13 to 21, this distance is 8. So it's getting progressively larger, and it's going to keep getting larger and larger and larger, and therefore it diverges. So this diverges. So because ln, we know ln is a function, this is we have ln 1 equals 0. So this keeps going to infinity as explained before. So if we're taking ln, if we take 4n squared well, these inputs right here are getting larger. So basically the input now is on the x-axis. This is our new input. So the inputs go on the x-axis, and then the output goes along this axis. So as this tends to infinity, we know that this value, whatever is in the numerator, it tends to infinity. It gets larger and larger. So therefore, if this goes towards infinity, then the y goes towards infinity, because if this is an increasing function, it's always increasing. So if it's always increasing x, it's always going to increase in y to the same direction. So therefore, the limit or diverges. So that's the key for this case, is it's always good to represent the numerator, try to represent the numerator as a function of the denominator. Start with the inside, work towards the outside usually if you want to break it, because then once you understand what the input is doing, then you can understand the output if you understand how the function ln behaves. And that's all and there you have it. So anytime working with sequences in series, it's important to understand just how the variables relate, and how you can, of course, there's some manipulation that can be done to simplify everything, and then you just go from there. So I'm going to end, this is the end of the series, and then I'm going to cover another midterm exam. This is this midterm exam A, and then I have another one I'm going to call B, or midterm B. It consists of about really 14 problems as well, and then I'll try to do that in a set of 3 or 4 videos. And yeah, that's all I have for now, and hope you enjoyed.